Welcome. In this lecture, which has multiple sessions, we'll explore a way to estimate the location of a minimizer for a function that has a vector argument. The main concepts that we'll go through is we'll first look at what a descent direction is, then we'll look at some of the convergence criteria we might use. We'll explore steepest descent using a constant step size and then using backtracking. The sample problem that we can consider is, suppose that we have only a local view of some physical terrain and we want to find a river in a valley. So, for example, suppose that we went out hiking and we used an automobile to get there and we left our automobile near a river. And at some point, we just don't know where we are. And you can imagine being dropped into some hilly terrain. And if you want to get down to the bottom, one way is to simply say, wherever I am, let's go in the direction that is steepest. And that would be a steepest descent. It might turn out that we are here and our automobile is over here, and it might be that the shortest path involves going uphill, but we're not going to look at that more complicated situation right away. We'll imagine that what we do is, even though it may take us a little while longer, we're going to use the steepest descent and eventually we'll get to where our automobile is. So this is the concept that we'll be exploring, which is descending to a minimum, and specifically descending to a point that is a minimizer. Now, let's state our problem. The problem is, suppose that we are given a function that has a vector argument and produces a real level, or we might write that in functional notation. The minimum level, so the minimum level is the minimum over all vectors that are in the vector space of the function. And this min over all of the possible vectors, this would return the minimum level or the minimum evaluation of the function. In optimization, we often are not particular about what that level is. What we want to know is, where does the level occur? For example, in our hilly terrain, the exact height above sea level isn't of particular interest. What we want to know is, where is our automobile? That is, we want the location of the minimizer. So the minimizer, let's call it the minimizer location. That is some stationary point, and that stationary point will be a different thing. It'll be the argmin, and argmin is the argument that gives you the minimum. So here it's what is the minimum level, and here is what is the argument, what's the vector argument that gives you that. And so we would write the argmin over all vectors in the vector space of the function that we're interested in. So what we'll do is we will search. That is, we won't attempt to find an algebraic, for example, or a closed form solution, because in general these closed form solutions aren't available. So we'll search for a vector, and here we'll just say near the actual minimizer that we're after. So what we'll do in this is we'll iterate, and we'll ask the user to give us a first estimate of the location of that minimizer, and then we will compute a second estimate and a third estimate, and so on, and we'll continue iterating. So we will need, in order to do this, we'll need to be able to evaluate the function at any vector, and we'll also need to be able to evaluate the gradient. Now, there are some classes of problems where the gradient is unavailable, or the gradient has to be numerically estimated by the routine that we're trying to write. Here we're going to assume that the user can provide us with these three things: a first estimate and a function and the gradient one form of it. And then we'll converge our convergence. This can get quite complicated quite fast. What we'll do is we'll loop while, and we'll say while that iterant is less than some maximum value of an iterant, and we'll say that so the user now has to provide us this. That's basically so that we don't go into an infinite loop. And then the user will also have to define something which we can colloquially call flat enough, right? So when is the gradient flat enough that we can stop? And so we'll ask that for the gradient that is evaluated at the kth iteration, we'll ask when is the magnitude of that gradient less than some maximum that the user supplies to us. So what we'll do is our search is, so at iteration k, what we'll do is we'll find a direction, and we'll denote that as the vector d with the subscript k, and a step size. And that step size we'll denote with s sub k. Back in scalar land, this was simply the negative of the derivative. And now in vector land, that's a more complicated notion. Here, the step size was either a fixed step size that the user provided us, or we used backtracking. So the search that we'll conduct is specifically, we will say we'll take the kth estimate of the minimizer, and we'll add the kth step size times the kth search direction, and that will equal our new estimate of where the minimizer is.